What if I told you that a regular high school physics exam paper could actually unlock the secrets to how our entire world is powered? It might look pretty ordinary, but buried in these questions are the links between everything, from a gigantic hydroelectric dam all the way down to just boiling a kettle for a cup of tea. Okay, let's get into this. So we're going to tear down this AQA GCSE Physics paper, but not for a grade, no. We're doing it to really get our heads around the fundamental ideas of energy and power that it's talking about. You're going to see how the very same rules apply on a massive national scale and then right there in your own kitchen. All right, first up, let's think big. And I mean really big. We're talking about the huge, colossal challenge of making enough electricity to power entire cities, all our industries, and millions of homes, all at the same time. This here is a classic example, pulled straight from the exam paper. All that water held back in a reservoir, it's packed with an incredible amount of gravitational potential energy. And when you let it flow down through those turbines, that potential energy gets converted into kinetic energy, the energy of motion, and then, finally, into the electrical energy that powers our lives. It's one thing to talk about these ideas, but the numbers involved are just staggering. And that's what's so great about this exam paper. It really forces you to face the sheer scale of it all. Just look at that number. That is 27 trillion joules. According to question 3.4 in the paper, a power station like the one we just saw can transfer that much energy in only 5 hours. It's almost impossible to wrap your head around, but that's what it takes to keep a country up and running. Okay, now here's where it gets really interesting. This graph from the exam shows that we don't use the same amount of electricity all day long, not even close. It takes a nosedive in the middle of the night, and then, bam, it spikes in the evening when everyone gets home. So the power stations have to be ready to handle these massive swings in demand. And that whole challenge of meeting the demand, well, that brings us to some pretty tough realities. Where we get our energy from really matters, and this exam paper doesn't pull any punches. It connects the physics directly to the real-world environmental impact. What the paper does here is pretty clever. It puts two crucial bits of data side by side. The chart on the left shows a clear trend in the UK, moving away from coal and towards natural gas. And at the exact same time, the graph on the right shows the undeniable upward climb of sea surface temperatures, a major red flag for climate change. So why the big switch to gas? Well, question 4.2 gives us a few clues. Compared to coal, burning natural gas pumps out less carbon dioxide for the same amount of power. Plus, it doesn't leave behind a bunch of solid gunk like ash. And, maybe most importantly, gas power stations can be fired up way faster to meet those sudden evening spikes we saw on the graph. Okay, time to shift gears. We've gone big, looking at the national grid. Now, let's go small. I'm talking kitchen counter small. Because the very same laws of physics that run a massive dam are also at play when you make a simple cup of tea. This is the focus of question 7 in the exam. It's a graph that shows the temperature of water in a kettle as it heats up. And let me tell you, this simple little chart is packed with information about energy transfer, heat capacity, and power. It's basically a perfect little physics experiment right in your kitchen. Now, if you look really close at that graph, you'll notice something weird. For the first 15 seconds or so, the line is totally flat. The temperature doesn't go up at all. So, what's going on there? Why the delay? The exam wants to know the reason. And the answer, taken word for word from the official mark scheme, is beautifully simple. The energy doesn't just magically appear in the water. First, it has to heat up the kettle itself, and more specifically, that metal heating element at the bottom. Only when that's hot can it start passing its energy along to the water. Simple as that. Okay, let's actually run through this calculation. It's not as scary as it looks. First, we just look at the graph to find the temperature change. It starts at 22 degrees and ends at 100, so that's a difference of 78 degrees. Simple. Next, we take our main formula and just shuffle it around to solve for mass, which is what we want. Finally, we just plug in the numbers we know, 155,000 joules divided by the other two values, and we get our answer, 0.47 kilograms. See? All the clues were right there in the graph. All right, the last part of this question is the real kicker. It's about power, which is just the fancy physics word for how fast energy is being used. The question asks how you'd figure out the kettle's useful power output. And the secret? Well, it's hiding in that straight, sloped part of the line. The steepness of that line, what mathematicians call the gradient, that's the key. It literally tells you how many degrees the temperature is shooting up every single second. And since we know power is all about energy per second, you can see how they're connected. If you figure out that gradient and multiply it by the mass and the specific heat capacity, you get the kettle's actual power output. It's this amazing direct link between the shape of the graph and a real-world number. So here it is, the big takeaway. Whether you are dealing with trillions of joules pouring out of a dam or just a few thousand joules to heat up your tea, the physics behind it all is exactly, and I mean exactly, the same. This is the big one, the law of conservation of energy. It's the one golden thread that connects every single question in this exam. Energy just changes its clothes. It goes from potential to kinetic, from electrical to heat, but the total amount of energy in the universe never changes. It's the fundamental rule, whether you're looking at a galaxy or a teacup.
So, at the end of the day, this exam paper is about more than just passing a test. It gives you the tools to understand the massive systems that run our modern lives, the really tough choices we face about our planet, and the trade-offs we have to make every day. It's not just physics, is it? It's about understanding the world,